Next, we will summarize all the strategies for integration. The first thing one should try is to simplify the integrand and possibly use the linearity of the integrals to split the integral into several simple ones. For example, let's integrate the following function. We can divide the numerator by the denominator, and this simple step turns the original integral into the sum of very simple integrals, whose antiderivatives we already know. One of the simplest integration techniques is a substitution. When integrating, make sure not to miss an obvious one. For example, in the following problem, we recognize the pattern and rearrange the integrand. Then set up the substitution by setting a new variable, let's say t, equal to 1 plus x squared, and finding the differential of t. Next, we plug everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function back for t. One can also take a formal approach to integration and start the process by classifying the integrand. For example, we developed many different integration techniques for integrating trigonometric functions. In the following problem, we have a trigonometric function and we recognize an opportunity to implement the split and substitute technique by splitting away a cosine of x and then setting up the substitution by setting a new variable, let's say t equal to sine of x, and finding the differential of t. Next, we plug everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function of x back for t. After using the reciprocal identity, we can rewrite the answer as negative cosecant of x. We also developed integration techniques for integrating rational functions. In the following problem, we have a rational function which, after factoring the denominator, can be decomposed into a sum of two simple rational functions, whose antiderivatives we already know. We also learned how to recognize certain patterns in radical functions. For example, in the following problem, we first recognize the distinct pattern, and then we set up a substitution by setting the variable x equal to secant of theta and finding the differential of x and the radical expression in terms of theta. Next, we plug everything into the original integral and simplify so that we have nothing but a trigonometric function of theta left in the integrand. We continue with the process by finding and simplifying the antiderivative of the trigonometric function. To finish the process, we need to replace theta with the original variable. To find theta, we consider the substitution and isolate theta by applying the arcsecant function to the both sides of the equation. To find the tangent of theta, we construct the reference triangle for angle theta, find the missing side using the Pythagorean theorem, and use the definition of the tangent to express it in terms of x. We finish the process by replacing theta and tangent of theta with the expressions in terms of x and simplifying the result. We also have explored the integration of functions with the radical of a linear expression in the denominator. Let's do an example. We set up the substitution by setting t equal to the radical of x minus 1 and finding the differential of t and expressing x and dx in terms of t. As a result, we have an integral in which some expressions with x get cancelled, but what's left we replace with t squared plus 1. Once we only have t's in the integrand, we continue with the integration process by finding the antiderivative and then replacing t with the original expression in terms of x. Sometimes it takes a bit of a manipulation to turn what appears to be a hard problem into an easy one. Let's do the following example. After multiplying the numerator and the denominator by 1 plus sine x and using the Pythagorean identity in the denominator and distributing the denominator over division, and then using some trigonometric identities, we have turned the original integral into the sum of the very simple integrals, whose antiderivatives we already know. In general, when dealing with unknown integrands, we try to relate the current problem to one of the previous problems that we already solved. Let's do an example. We rewrite the integrand as a product and choose u and dv, and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the integration by parts formula and produce a new integrand, which we already know how to integrate. When none of the methods worked, try again. If one substitution didn't work, then try a different one. If the integration by parts didn't work, then try different choices of u and dv. But remember that at the end of the day, there are still functions whose antiderivatives we can't find in closed form. Here are a few examples of such functions. We discussed and practiced different integrating strategies that cover a variety of functions.